where T is the temperature, R is the gas constant, and gamma is the specific heat ratio, right? And now remember, if the temperature is very low or very different or very high, the Mach number can be very different. And in rarefied flows, the Mach number definition changes quite a bit. In fact, our Mach number calculation, the Mach number goes to 10,000 almost, 9,000, which is very unrealistic behavior of material. In fact, Mach number definition does not really apply in that region, because if you look at the standard, the thermodynamics that you learn is called classical thermodynamics. It is all based on continuum. That is, you don't have particles going around. When you go to quantum mechanics or discrete mechanics, there is no such thing as temperature. There is just the kinetic energy of molecules. And I don't know if you have learned the statistical thermodynamics. If you take a course or subject on statistical thermodynamics, you will know that there is no such thing as temperature at that level. You just talk about kinetic energy and other energies, potential energy, and so on. So Mach number is really, not a realistic way of looking at it. But that is where you start. And so when we started this, we were really puzzled as to what to do in terms of writing the equations and putting the equations together, because it was not just continuum mechanics here, but it was all kind of more like quantum thing, particles going around and so on. We did many attempts at it. This figure kind of nicely summarizes what are the different regions that you're looking at. This is that Knudsen number, it's a saturated Knudsen number. They've defined in a certain way. This is the pressure. And what it is saying is that there is continuum region when it is low Knudsen number, and then there is a free molecular region. That means the molecules just go freely, they don't even collide with each other. Before that, this transitional region where they collide quite a bit. Then there is a slip continuum region where you might remember in fluid mechanics, when there is flow going over a solid object, such as this object, if I were to blow, or if fan is blowing air on this surface, the boundary condition at the surface is, what is the speed? Speed is equal to 0. That is, speed is actually same as the solid speed, which is 0 in this particular case. The reason it is 0 is because it is a no slip condition, if you remember from fluid mechanics. Well, when you go to molecules, a particle level, it is not exactly 0, because the particles may just skip, just hit and come out. And so the speed is not 0, exactly, speed of, it continues, and there is a slip continuum region. So when it is rarefied, when it's low density region, there is some speed that can occur even at the solid boundary, which is another complication. And then of course, when it is transitional, then it becomes very complicated, in the sense that what we are studying is that when the molecule of this one material that is going, and if it hits the substrate, usually it will get deposited. It won't even get reflected, but sometimes it may, or so on. So we had to somehow model the whole thing. Basically, my student, poor Kevin, he was working on this for many years, pulling his hair how to do this, and we are going back and forth, and because it is not there in any of the books, it is his own PhD thesis. And so for titanium, we got all the equation of state and everything, because we're looking at titanium vapor. Titanium is very high temperature. So this is computational fluid dynamics and direct simulation Monte Carlo solver. For basic equations, we used a program called OpenFOAM. Does anyone know what is OpenFOAM? Has anybody used OpenFOAM? If you haven't, I would highly recommend you to do that, because first of all, it costs nothing to use it. And it is probably the most powerful fluid mechanics type of program that is there. I would say it is more than, personally I like it better than Fluent or other programs, which cost $50,000 sometimes per year to lease them or to rent them. OpenFOAM is open source code. So you can get open source code and you can change the code the way you want. And you can add things. So we wanted to add, it's not just fluid mechanics, we want to add the Monte Carlo simulation in that, and so on. So this is the basic equations, the CFD equations these are kind of well known, Navier-Stokes equations and all that. The continuity equation, mass conservation, momentum conservation equation, Navier-Stokes equation, these are all vectors, so they are x, y, z, three directions. And then there is the energy equation, and then constitutive equation is the equation of the state for the gas, or the way the properties are connected. And there's heat flux equation. So there's a basic set for fluid mechanics. This is well known, this is well programmed into the system. For direct simulation Monte Carlo system, where we have now particles which are going around, you cannot use a continuum equation, you use the so-called Boltzmann equation from physics. And so in this equation, what you do is you have a probability density function f, which says that the probability of having f, density of f, depends on the time x, y, and z, the space coordinates, the time coordinates, and also the speed. That is, the probability of finding a molecule between t plus delta t and x plus delta x, y plus delta y, z plus delta z, and speed of v plus v and v plus delta v is so much. And then you integrate it over space and so on, and find out how it is. That's called Boltzmann equation. It's a very well known equation. You can go back there and solve it. And then there's a way to go back and forth. I won't go into that very much, but I guess the main thing is that how do you take the particles and how do you make sure when they collide with each other? The collision can be of different types. Either the particles, when they collide, they can make a bigger particle, they get together, or they may collide and go away, or something in between that can happen. Same thing happens when they collide with the surface, where they get absorbed or they don't get absorbed. So there are, in the past, people used a certain way. Now remember in that figure where we have continuum mechanics and then there is direct simulation Monte Carlo or particle regime. In between there is an interface, and how do you handle the interface mathematically, right? From equation point of view. So people have come up with certain ways of ghost cells and so on. So my student came up with a very interesting technique actually, and then the idea was that how do you patch different regimes, and let me go here. Okay. So this is CFD region, no problem, you can calculate it. This is a DSMC region, you can do it. But what happens at the interface? On one side there is continuum mechanics, the other side there is not. And where it meets, and how do you define that? How do you find out? Because it's not given. You have to mathematically find it. And so what kind of boundary condition you will use, and that was the biggest headache in the whole. So basically we came up with, and I had to credit my student, he did a good job in that, how he matched the density and the particles and went on checking whether the boundary, what is the boundary. On one side of the boundary there is CFD formulation of equations, on the other side of boundary there is direct simulation Monte Carlo technique, and you go on defining the boundary. Basically that is how he calculated that. It becomes highly numerically intensive, and then this is the overall flow chart that you initialize that, and then you go do the CFD calculation, and then you go into DSMC region and you do the calculation and you check whether it is still continuum region or not. If it is continuum region, you go do CFD and you keep on doing. If it is not continuum region, you call it direct simulation, then you stop there and define a boundary there, and you go on defining the problem from there. And then finally we have some comparisons. So what we did was, going back to our coating problem, if you do only CFD calculation, what results will you get? If you do only DSMC for the whole thing, what results you will get? And then if you go hybrid, that means part CFD and part DSMC, which was not done before with the right kind of boundary, this is the first time we have, Kevin and us, we have done it before. So if you just do this, and if you have different parameters, And if you vary the different parameters, you find that in which parameter range the fluid mechanics works, which parameter range DSMC works, and then how do you patch it, which way hybrid works. And that he did, the parametric study, which is each run would take days, by the way. I mean, a simple run would, and that is not on a small machine, on a cluster of some 256 computers connected together. And it's a kind of major kind of thing. And so I have the CFD studies. I shouldn't flip the slides quickly, but this is computational fluid dynamics study, and then for different boundaries and pressure gradients and all that, we tried that for the whole region. Then for DSMC, we tried for the whole region, and then we looked at hybrid for the whole region, where part of it is CFD, part of it is DSMC, and the boundary is automatically calculated by the program, which is a very, very interesting thing. That by itself, the program keeps on working back and forth and decides, okay, this is where the boundary is, and it works. And then we did some comparison. First of all, we had to do validation. As I said, a lot of slides I borrowed from my students' PhD defense. We went over this many times, and so you have to, when you do a computer program, the biggest problem with any computer program is that if you put an input, it will give you an output. It could be total garbage, but it will give you an output. Then you decide, okay, well, is this reasonable or is correct or not? How do you know that? So you go on doing different checks. One is that you try it with a known solution, or you can also do the mesh independence. That is, you increase the mesh size, and see whether it is independent of mesh, because the result should be independent of what assumptions you make there in terms of mesh. So we did different kind of validation studies for different geometries for known results, and basically when it checked, we went ahead. When the thing compared, we went ahead. This is for computational fluid dynamics, flow field, and for different parameters. I'm not going to go over this. This is the DSMC I was saying. DSMC is the particles. So what you have is the particles going around all over. It is not continuum mechanics. It is what we had to do, or what Kevin had to do there in this, is that he had to model how the collisions took place and what kind of collisions, and that was programmed in fully, and that was added to the open form. Basically this software package goes on growing, and you finally compare. I will kind of quickly go different hybrid shapes to begin with. I will just, and then we compared this results with experimental data we got from somewhere. This Mukherjee and some other paper, they had done this, and based on all that, and so they had a different material, copper. So you have to get copper data and copper everything, and then study that, and there's geometry is different. But I will just jump to, we did it with all three hybrid, computational fluid dynamics, DSMC, and hybrid, the two together, two separately and one combined. That we develop an improved physical vapor deposition material model, and the results, for rapidly rarefied flow. That means the flow is dense at the source, but goes on rarefying. It becomes sparse, and under certain circumstances, after we created the hybrid solver using base computer, base software package of OpenFOAM, although all the hybrid stuff is including the computer software that we added to the OpenFOAM, and there are certain regions that basically this is important. The hybrid CFD DSMC solver displays certain virtual source characteristics. That is, if we have, if this is a chamber, and if it is the source where the material is coming from, it is as if there is an imaginary source somewhere above that where mass is coming from and is going in all directions, and then what will happen is what it looks like using this, and you can prove this. Going back to the application, so why do we do this mathematical model? Why do we go through all this trouble? Because with mathematical model, we can basically do all the experiments at our desk using a computer. We go through all these different scenarios, and then we find out, well, this experimental way looks like what comes closest to what we want. Because each run may end up costing you $1 million to do everything and test it and so on. So instead of doing $1 million run every time, you do modeling and then you pick the optimal conditions and then you do the runs after that. So my email ID, actually it's an extremely easy email ID. It has only total 11 characters, but my initials, AKK, Anil K. Kulkarni, are my initials. AKK @ PSU for Pennsylvania State University .edu for education. So akk@psu.edu. Feel free to send me an email. When you send me an email, in the subject field, write that you're from whatever we met at GTU or something, because every day I get 100 emails from students all over the world. Well, thank you very much. It's all done. Thank you.